In this video, instead of focusing on a specific command, we're going to talk about something fundamental, the file permissions. Understanding how file permissions work will make every other shell command video much easier to follow. File permissions are at the heart of Linux security. They define who can access files and directories and how. To view them, we use the ls command with the L option. You can also use ll if it's set up as an alias on your system. We talked about that in the ls command video. It shows a detailed listing of your files, including their permissions. Let's break down the output. The first field in the lsl output displays a group of metadata including file type, permissions, user owner, group, and extended attributes. We won't go into file type or extended attributes in this video. In this example, however, the initial dash indicates that contents is a regular file. Directories are represented with a D instead, just like we see here in the Documents directory. There are other file types too, like L for symbolic links or B for block devices, but regular files and directories are by far the most common. Now let's have a look at the permission string. This 9-character string represents 3 sets of permissions. The first set is for the owner of the file. The second set is for the group, and the third set is for other users. Every file in Linux has these 3 sets of permissions. Note that by default, when a new user is created, a group with the same name is automatically created as well. So in our example here, we see different permission set for the user lab user, which is the owner, for the lab user group members, and for all other users. Now let's take a look at how Linux checks permissions and in what order. When you access a file, Linux first checks if you're the owner. If yes, it applies the owner's permissions and stops there. If not, then it checks whether you belong to the group that owns the file. If you do, it applies the group's permissions. And if neither is true, the other's permissions apply. So these 3 sets are mutually exclusive. You can only fall into one category at a time. File permissions in Linux can be expressed in 2 formats, Symbolic Mode and Numeric Mode. In Symbolic Mode, we use letters, and in Numeric Mode, we use numbers. We'll start by examining Symbolic Mode and the meaning behind each letter. But first, let's define the user's categories. The U represents the user owner, the G represents the group, and the O represents all other users. Now, regarding the permissions categories, R stands for read, W stands for write, and X stands for execute. Let's explain each of these categories in the next example. We notice here that the owner's permission is RWX, which means that the owner can read, write, and execute the file. For the group, it's RW-, meaning that the group members of lab user group can read and write, but they cannot execute the file. The dash means disabled. And finally, all other users can only read the file. Now let's move to numeric or octal mode. This one uses numbers instead of letters. In this example, we will use the stat command in order to view the permissions in numeric mode. We notice 3 numbers here, 7, 6, and 4. The first represents the permissions of the user owner, the second for the group members, and the third for other users. In numeric mode, each permission has a value. Read has the value of 4. Write has the value of 2, and execute has the value of 1. To find out the permissions of each user classification, we simply add up their values. So here we can understand that the user owner has read, write, and execute permissions because 4 plus 2 plus 1 equals 7. The group members have read and write permissions because 4 plus 2 equals 6. And all other users have read-only access because the value is 4. If we want to provide no access at all to a specific user classification, we set the number 0. We've seen how file permissions are displayed, now let's see what they do. Let's first switch to lab user, who is neither the root user nor part of the root group, so the permissions defined for others will apply. In our case here, read only. Read permission allows you to view a file's contents, for example using commands like cat as we see here, or the less command, or even with a text editor such as vi. Also, read permission is required when we want to make a copy of a file. Now, the write file permission is required when we want to modify the contents of the file, either by using a text editor like vi, or by overwriting the file entirely with commands such as cp or mv. We can also edit the file's contents with shell redirection. In our example here, we use the single greater than symbol to overwrite the file's contents. In general, without this permission, you can't make changes to the file's contents. And finally, execute file permission lets you execute the file contents. This permission is required when we want to run binaries or scripts like bash or Python files, for example. When we run the execute file here, which is a bash shell script, we can see that it prints some text to the standard output. A small tip here is that you can still run a script with no execute permissions through an interpreter like bash, since it's bash doing the execution. As we see here, we managed to execute the myscript.sh without having execute permissions on the file. Directories have permissions too, but they behave a bit differently. A directory is marked with a starting D as we saw earlier. Now let's see how permissions works for directories. Read directory permission lets you list the directory's contents, for example with ls. As we notice here at the bottom, we can list the contents of the directory, but we do not have access to view the metadata of the files inside. Write directory permission allows you to add, edit, or remove files in that directory, such as creating files with touch, deleting with rm, moving files in with mv, or edit the contents of a file with file redirect operator. As we notice here though, we cannot do any of that unless we also have execute permission on the directory, because the permission to manage the file's metadata inside is required. Now, execute directory permission allows you to change your working directory to that directory by using cd. Look at extended information on files in the directory by using ls-l, or even change the directory's contents permissions. Remember that execute permission impacts the other two permissions. As we saw earlier, even with write permission on a directory, we couldn't create a file inside it because we didn't have execute permission, which is required to access the directory's metadata. Now we will see how to modify permissions using the chmod command, short for change mode. Let's create an example file first. In Numeric mode, we will type chmod, the permissions we want to provide for owner, group, and others, and then the file name. In symbolic mode now, we will type chmod, the desired user classification, U for user owner, G for group, O for others, or A for everyone. Then we will add or remove the permission we like, and finally, we will type the file name again. Here, for example, we add read, write, and execute permissions to the user, owner, and group. Also, we add read permission to all other users, but we remove the execute permission from them. Other users didn't have execute permission in the first place. The last command was a quick demo to show the access removal. Let's quickly switch back to the root user by exiting from the current shell. Now, if we want to change who owns a file, we should use chown to change the file's user owner, or chgrp to change its group. For example here, we changed the user owner to lab user and the group to lab users. We can also change both with one chown command by defining both the user owner and the group separated with the colon symbol. As we notice here, the ownership changed back to root. Linux also includes special permissions that extend beyond the standard read, write, and execute rules. The first special permission is SUID, which stands for Set User ID. It's a file-level permission that makes a file to run always as its owner, no matter who executes it. The main purpose of setting SUID is to allow regular users to run specific files that require elevated privileges without giving them sudo access. We can assign SUID permission on a file in symbolic mode with chmod u for user owner plus s, which stands for special permission, and then the file name. Remember that SUID can be assigned only on files. Or in numeric mode with chmod 4 for SUID, the rest of the permissions afterwards, and then the file name. We can identify if SUID is set by checking the user permissions if there's an S where the execute would normally be, as we notice here. One good example of the SUID is the passwd binary file. This file is used when a user needs to change their password by modifying restricted by regular users files, like etc shadow. This way, any user can execute this binary with the privileges of the root user. The binary itself, though, is designed so that a regular user can only change their own password while only root can change passwords for other users. But the file permission part is managed by the SUID. Keep in mind that on all modern Linux systems, the kernel intentionally ignores the SUID and SGID special permissions on interpreted scripts like Bash, Python, Perl, etc. for security reasons. The second special permission is the SGID, which stands for Set Group ID. It's a file and directory level permission. When set on a file, the file runs as the group owner, but if set to directory, files created under it inherit the directory's group. This is helpful for directories used collaboratively among different members of the same group. Let's see a use case. Imagine we have 10 users named lab user 1 to lab user 10 as we see here, and we want all of them to have the same permissions on files inside the lab directory, no matter who creates them, but provide no access to all other users. To achieve this, we added first all of them to a common group called lab users and changed the umask for these users to 007. We won't go into umask in this video, that's a topic for another one. But just keep in mind that umask sets the default permissions for newly created files and directories. And in our case, we set, by using the number 7, no permissions to all other users. So now let's set the group ownership of the lab directory to lab users. Next, we apply the SGID permission to the directory. This ensures that any new files created inside the directory automatically inherit the lab users group instead of the individual creator's default group, by typing chmod g for group ownership plus s, which stands for special permission, and then the directory name. The S letter here at the third position of the group permission section indicates that the SGID is enabled. If we create a file inside the lab directory as lab user 7, we'll notice that the file's group ownership is lab users instead of lab user 7. This means that all members of the lab users group can now read and write that file, and all other users have no access. We saw in the use case how to assign the SGID permission in symbolic mode. In numeric mode, we do it by typing chmod, followed by 2 for the SGID special permission, then the rest of the permission digits, and finally the file or directory name. The last special permission is the sticky bit. It is a directory-level special permission which ensures that only the file's owner can delete files under that directory, even if they have write access. We can provide StickyBit special permission with chmod plus T to add StickyBit and the directory name in Symbolic Mode. And we can verify that the StickyBit is enabled by the T letter at the end of the file permissions block. In Numeric mode, we type chmod, 1 for StickyBit, the rest of the permissions, and then the directory name. So now the file can be deleted by the owner and by root users only, even if read, write, and execute permissions exist for all other users. So there you have it, Linux file permissions explained. We've seen how to view them, how to interpret them, what they actually do, and how to change them when needed. Understanding permissions is key to mastering Linux, not just for security, but also for avoiding those frustrating permission-denied errors. Did you like the video? Let me know in the comments. If you found this helpful, don't forget to like, subscribe, and check out the other Shellye tutorials for more Linux command breakdowns. Thanks for watching, and see you in the next one.